Hello, everyone. It is on the dot 1700 GMT. Usually people still sort of join us over the next couple of minutes. So we'll give it another minute or so before we hand over to today's speaker. In the meantime, if I could please ask you to keep your microphones muted and your cameras off for the duration of the presentation. Afterwards, when we get to question and answer session and you do have a question that you want to ask in person, you are welcome to unmute and even switch your video on and ask directly. So as we get ready to start, please share in the chat where you're tuning in from around the world. It's always interesting to see where people are joining from and who we are reaching with these seminars. I'd also like to remind you that the seminar is being recorded and that the recording will be available on the SCB's Vimeo site in a couple of days after the actual event. So I see we've got somebody from Davis, California, Mark Schwartz. Welcome, Mark. Dick Carr from Oudtshoorn in the Western Cape of South Africa. A couple of regular attendees here. So welcome to everybody. So I think we can start, and I'd like to welcome you to what is now the 18th seminar of 2021 in the Society for Conservation Biology's Emerging Issues in Conservation seminar series. In the series, we feature articles selected by the editors that are recently accepted, like tonight's paper, or in early online view, or recently published in the 3 SCB journals, those being Conservation Biology, Conservation Letters, and of course, Conservation Science and Practice. My name is Martin Strauss, and I will be hosting today's seminar. I'm a senior lecturer in the Department of Environmental Science at the University of South Africa, and I'm also an associate editor at Conservation Science and Practice, and I've been organizing the 2021 seminar series to date. So before I introduce our speaker, please note that you're welcome to post comments and questions in the chat. And then should you prefer, you're also welcome to ask your questions in person during the Q&A session at the end of the seminar. So it is my great pleasure to introduce you to Dr. Kyle Horton, our speaker for today. Kyle received his BS in biology from Canisius College in 2011, his MS in wildlife ecology from the University of Delaware in 2013, and PhD in ecology and evolutionary biology from the University of Oklahoma in 2017. He was a Rose postdoctoral research fellow at the Cornell Lab of Ornithology from 2017 to 2019, and is now an assistant professor at Colorado State University in the Department of Fish, Wildlife, and Conservation. His lab's work on migratory birds employs a range of tools and approaches, including the use of radar, acoustics, and community science data. He's currently working on uniting these pieces of information together to better understand how migrants fill the nighttime airspace, determine where and when migrants are impacted by artificial light, and how radar can be used to forecast and mitigate these impacts. And with that, Kyle, over to you.
Thanks so much. Thanks for the introduction, and thanks everyone for tuning in today. So yeah, as Martin said, I'll be talking about a recent publication entitled Near-Term Ecological Forecasting for Dynamic Aeroconservation of Migratory Birds. However, this paper falls into probably a number of years of work that has been coming together. So I'll try to give a full arc of some of the things that we've been tackling, primarily using radar data, but within the scope of what we call aeroecology, so the study of aerial organisms and how they use the lower atmosphere. So today I'll be talking about some of the conservation implications of that work, particularly in the realm of light pollution. So I'll try to give some background, probably with the expectation that not everyone's a radar ornithologist or an ornithologist, so I'll try to give a little bit of background on bird migration in North America, and then talk about how we're using radar data to really tackle these conservation challenges. So, thinking about the players of, what are the species of migratory birds in North America, it's quite diverse. So hopefully you get a little bit of an appreciation for this, just going through, slides of, pretty migratory birds in North America. But it's really challenging to, come up with tools, techniques to capture this diversity, right? So sometimes tracking studies are done on these type of species, but when we're talking about, broad front movements that scale to hundreds of species to millions, if not billions of birds traversing north and south across North America, it does require a little bit of a different suite of tools, and that's what I'll be talking about today. But sort of more generally, right, how many migratory birds are out there? How many birds in general are out there? So of the roughly 10,000 or so species globally, about 19% are considered migratory. And that number can probably go up a bit depending on how we classify bird migration. But nonetheless, suffice it to say, migration is not a very unique trait, right? Many species do it across the world. Today's talk will be very North American centric, if not US centric, and it'll probably make sense of why that is, but it's really tied to the tool that we use. These radar data are generally run by government agencies, and that's the tool that we use is run by the US government. So in North America, you could probably expect that if we were to say what's the percent of species that migrate, that metric's going to be a good bit higher, just given temperate latitudes, birds getting pushed in and out of broad regions just based on climate variation. So about 70% of species in North America are considered migratory. So some of those are long distance, some are short distance. Some might go up and down in latitude, some might go up and down in altitude or elevation, running up and down mountain slopes, for instance, spring and fall. But another challenge here is that when we think about the species that migrate in North America, for instance, 70%, we can then go ahead and classify those. When do those birds migrate? Particularly, do they migrate during the day? Do they migrate at night? And this is probably, maybe quite obvious to most here, but sometimes it isn't. So of the 70% of birds that migrate in North America, 80% are moving under the cover of darkness, migrating at night. So in terms of broad monitoring, this is a challenge, right? We can't really rely on visual observations. We can't really leverage community science observations because we can't see what's going on. So we do require a different suite of tools. And the tool that we use to capture the movements, the direction, the speed, the intensity of migration is using large-scale radars. So I'll walk through some basics of radar to get you acquainted a little bit with what it looks like, the scale that it's happening, and then where the radars are positioned throughout the United States. So this image here, we can just walk through this one slowly. So this is what we're going to see is a little video, and it's going to be a series of essentially radar scans. They're going to come in every 5 and 10 minutes. That's going to be the update time. And the video will largely start around sunset. And then just to orient yourself here at the north end or the top of this slide here, you can see Florida. So we're looking at southern Florida, and then just at the bottom of the slide here at the southern end here is Cuba. And then right here at this white dot exists a radar, a weather surveillance radar. It's called KBYX. It's in Key West, Florida. So what I'll show you here is as the sun sets, these birds are going to take off. So you're going to see this wispy stuff start showing up, coming off of these islands in Key West, Florida. And those birds are heading north during spring migration. And then you're going to see a large secondary wave of birds coming out of Cuba, making their northbound journey into the airspace of the United States or into the airspace of Key West, Florida. And then ultimately sort of fizzling out, making landfall as the sun starts to rise. So hopefully you'll get an appreciation for just the magnitude and scale of this. So you can see, it'll loop around a couple of times here, but you can see as the sun sets, right about now, we get some birds taking off from the islands and then a big wave of birds taking off from Cuba, the island of Cuba. So this is going to be made up of, probably many dozens of species. And we're talking here in terms of the scale of number of individuals, sort of on the scale of hundreds of thousands of individuals, if not millions of birds flying through those airspaces. So this is just one night, it's one radar. We have radars across the United States. There's 143 of them that you can see here. And these radars collect freely accessible data. They're updated every 5 or 10 minutes. And usually they're processed in a way that you just get to see this. Let's say you went to a website and you wanted to look at the radar data, today. You typically see something like this. This image here is from a couple of years ago now, but all of the stuff that's showing up here is largely precipitation, weather events. Meteorologists work really hard to just show you this, but the reality is the raw data looks something like this. So the stuff that just popped up is largely biological activity, and in this case, migratory birds. So what we do is really the inverse of what most meteorologists try to do. We go ahead, we remove all of the rain, the precipitation. To us, that's basically clutter. We remove that and then maintain the biological product, again, the birds. And then we do this, for every 5 and 10 minute scan, but we don't do it just for one site. We do it for all 143 sites now. And we do it for many years. So you'll see this as we go into the talk. We've compiled, basically more than 2 decades of radar data for some of these analyses. However, the reality is that these birds aren't really moving across a landscape that is devoid of structure, right? That might be, structure from actual structures. There's atmospheric structure, and then there's also structure in a sense from light pollution. So these birds have evolved for hundreds of thousands of years to migrate under the cover of darkness, using topographic features, using stars to navigate, and a whole slew of other reference points that have been disturbed in the last 50, 100, sometimes 200 years by light pollution. So what we're trying to do is utilize some of these radar data, these remote sensing large-scale products, to understand how light pollution may be impacting migratory birds, and then how we can come up with tools and strategies to try to mitigate that conservation issue. So I'm going to start at a small scale here with a couple of examples of how we can begin to understand sort of the mechanics of what's going on from a few very prominent examples. And then we'll ramp up in terms of scale back out to the US scale. So we're going to start in New York City. So New York City, the largest city, at least in the US, is heavily urbanized, but has urban parks, right? So we know, if you go during spring or fall, you go to an urban park like this, Central Park in Lower Manhattan, or Upper Manhattan, I guess. You'll find migratory birds. So they're clearly flying over these sites, but now from what we've already talked about, they don't necessarily make landfall when the city looks like this, but rather looks something like this. So they're making landfall into these urban parks during the nighttime. So coming into these areas when it's heavily photopolluted. We did a study now a few years ago, maybe 3-4 years ago, where we tried to understand the impact of a very prominent source of light pollution in Lower Manhattan, that being the September 11th tribute in light. So every September 11th, New York City puts on a memorial to remember the lives lost during the September 11th attacks, terrorist attacks in New York City. And this memorial is composed of these beams of light to really signify, the structure, the placement of where the Twin Towers once resided. However, on the grand scheme of, light pollution and the interaction of migratory birds, this timing generally overlaps with the peak timing of nocturnal migration during the fall or autumn. So this provided us a unique, sometimes a fortuitous experiment, let's say, of trying to understand what is the correspondence between these lights, their intensity, and the number of birds that may or may not be attracted to this light source. So for the last 10 plus years, sometimes longer, probably longer than that at this point, we've been going out and monitoring these lights during on the night of September 11th. And this is just a sort of toy example here, but what you're going to see here is a video I took maybe 4 or 5 years ago now, and I'm laying down on a platform looking up straight into one of the towers of light. So there's, each tower is made up of basically 44 spotlights that are cast, skyward. And hopefully you can see what look like, insects moving around are all migratory birds, actually. It's hard to tell from here, just given the magnitude. But these are largely composed almost exclusively of wood warblers, some of those colorful, long-distance migratory birds. And they're quickly attracted to this light source. So not all is lost here, but what happens here is when we detect about 1,000 birds in the beams of light, the beams are actually turned off for about 20 minutes to allow the birds to head south, trying to really mitigate some of the threats that these birds would be facing. However, we wanted to come up with a more objective way of just visually saying there's 1,000 birds to an objective way of using remote sensing data to say there's 1,000 birds or more. And that's exactly what we did. So we used radar data overlaid on the tribute and light. So this image here that you're seeing is a radar product known as reflectivity. We could just think of it as a gradient of number of birds in the airspace going from cool with the blues to warm with the reds, many birds. And what you can see here, this is an example of a radar image from September 11th, 2015. And the image, the remote sensing product, was collected at 10:12 p.m. And that's local time. So the tribute and light you can see here with this black dot. So just 20 minutes later, we get a new scan from the radar. In the leftmost image here, the tribute and light's actually turned off. So in this image, we're estimating around 500 birds surrounding the tribute and light. This is probably the baseline of just a good night of active migration, 500 birds. 20 minutes later, a new radar scan comes in, and in that duration of time, the tribute and light has been turned on. And this is what that new radar scan looks like. So in just 20 minutes, we're estimating over 15,000 birds now surrounding the tribute and light. And it's quite obvious where the center of attraction is, centered directly on the tribute and light. So this is a really clear example of how light pollution, specifically a light source, can attract and disorient migratory birds. Across basically 7 nights of monitoring across 7 years, we estimate birds coming in and out of this light source totaled to around 1.1 million birds. So it's definitely causing some sort of disturbance to these birds. It's not resulting in mortality. We don't see a tremendous amount of bird mortality at these sites, but that's also probably in part that the lights are turned off when we hit a certain threshold to mitigate the incidence of colliding with a nearby building, for instance. So our next question here was, again, as I said, we'd start at a smaller scale. Here, we started at New York City at the Tribute and Light. What we want to better understand is New York City sort of the worst offender for exposing migratory birds to light pollution, or is there a different suite of cities across the lower 48 states that we could begin to really categorize how birds are being exposed to light pollution and where the greatest threat is? So to do this, we looked at New York City, but also another 124 cities across the US. So the top 125 largest US cities. So here what we're looking at is the incidence of light pollution and number of migratory birds coming over these cities. And it probably makes sense of why we're focused on cities, but if not, I'll just sort of, bring that home. So the top 125 largest cities account for around 2.1% of the lower 48 states landmass. So a pretty small percent, but it accounts for just over 35% of all the light radiance or light pollution throughout the US. So it's quite disproportionate in terms of its footprint relative to light pollution footprint. Okay, so I'll keep the details short. If you do have questions, please ask at the end. I'm happy to jump into some of the details here. But suffice it to say that we ranked the top 125 largest cities for spring and fall. And that's what I'm going to show you on this plot here. So on the y-axis, we're going to have a spring rank. So basically, you're going to see 125 points show up on this plot. They're going to be shaded. I'll describe what they're shaded by. But a point that resides at the top right of this plot is going to be generally a large city, a lot of light pollution, and many birds flying over that city. Something in the bottom left is going to be generally a small city, little light pollution, and not as many birds flying over that city. So this is the way things shake out here. So the size of the discs here, the circles, are scaled to the size of that city. And then the color of the point is scaled to really the light pollution level of that city. So some of these might be probably well known, at least globally. So something like Las Vegas is the brightest city in the US. By our measures, the second brightest was New Orleans. Any city that sits below that dotted white line within this green area tells us that the exposure at that city for migratory birds is going to be higher during the fall. And if it's above this line, the exposure is going to be higher during the spring. So sort of more birds flying over that city during that season. However, if we're really trying to, start with the greatest concern here, we might go right to the top of this chart here and try to figure out, what are the worst sort of offenders? And number 1, 2, and 3 are Chicago, Houston, and Dallas, and they didn't waver by season. So we started here with another example of how light pollution at a specific city in Chicago, how light pollution may be manifesting with bird collisions at a building. So another proof of concept here. So I'll just sort of show one slide here, but I would encourage everyone to check out this recent paper led by Benjamin Van Doren that came out in PNAS a few weeks ago. So in this paper, we looked at bird collisions at a single building in downtown Chicago. So you can see it as this little black box here, the area that we're going to zoom into. And this is sort of the urban sprawl of Chicago, and we're going to focus on this building that's highlighted in this coral red-orange color. And that building here is McCormick Place Lakeside Convention Center. So for the last 40 or so years, nearly 40 years, folks from the Chicago Field Museum have been going out and monitoring how many birds collided with this building, fatally collided with this building. We were able to leverage those data, link them with radar data as an index of how many birds are flying on a given night, but also at this building, the amount of lights or bays of windows illuminated were monitored. So we were able to look at a number of factors: bird migration intensity, light pollution intensity, and then we had a measure of mortality. And what we found in very brief order here is having the illuminated window area on McCormick Place decreased collision counts by 11 times in spring and 6 times in fall. So we found a direct relationship between the incidence of fatal collisions and the amount of light pollution on a single building. So trying to think about, why are these birds colliding? Light pollution being a factor here, but migration intensity was a factor that always showed up in our models, suggesting to us that we have a general ability to predict collision incidents based on how many birds may be flying on a given night. So if we are able to predict the number of birds flying on a given night, we might be able to give out a warning to say, turn off the lights on these specific nights. So what does general migration activity look like through a season, for instance? So I'm going to jump to my local radar here in Colorado, the Denver, Colorado radar. And what I'm going to show you is a spring time series of generally what migration activity looks like. And this is probably familiar to most of you if you have any relationship with migratory birds that may come through your backyard or your neighborhood or your favorite natural area, right? That there's a certain time of year during spring or fall when most birds are coming through. So this is an index of migration activity as measured by the radar. So you can see most of March, beginning of April in Colorado is pretty low in terms of biological movement, migratory movements throughout the state. We can isolate these sort of time series into individual nights, and then we can look at the low end, right? This is what the lowest activity looks like from a radar perspective. This is what the highest activity looks like from a radar perspective. So it's these high activity nights that are really important for trying to mitigate collisions at cities, buildings, etc. So in this season, it's just 3 nights account for 50% of migratory passage. And those 3 nights span about 19 nights. So this is just one example. It's for 2018 in Denver, Colorado. We can scale this up to all the years of the radar data that we have for the Denver radar, but all of the radars across the United States. And what we find is that most activity in the, let's say, bottom 50% of the nights really don't account for much biological activity. But it's the upper end here. It's about 10 nights in each season, spring and fall, account for about 50%, in this case, 54.3% on average activity will pass through in the top 10% of nights. And that generally equates to about 10 nights. So if we're trying to target these nights, or we would try to target these nights if we could predict activity on these few really intense movements. So this is a challenging problem, however. We need to quantify accurately and identify a small portion of nights that are particularly important for mitigation. So again, we're trying to predict the rare events out of, let's say, a season that might be 100 nights. We're trying to isolate the 10 where we see the vast majority of activity. Again, this is all predicated on, let's say, a building manager isn't willing to turn off their lights for 100 nights, for instance, but they would be willing to, say, turn off their lights for 10 nights out of a season. If we could tell them with a degree of confidence which of those 10 nights they are, that might have additional conservation traction. So there's sort of two camps in, at least two camps in approaches to lights out programs, right? We could turn off lights during a period of time. So again, that might be a whole season or it might be a subset of the season. But nonetheless, you make a blanket statement and it might be an example like this. For example, Denver turns off their lights from May 2nd to May 17th, a window that historically might capture 50% of the passage. We're going to call this fixed selection. So it's a fixed selection of nights that are going to get a lights out action, let's say. Or as an alternative, we could turn off lights during specific nights of high activity. So for example, Denver follows forecasted alerts. They might turn their lights off for April 28th, May 1st, May 3rd, May 4th, May 8th, for example. And we're going to call this dynamic selection. So we can use the radar data to basically monitor both of these metrics across the United States. That is, we're going to predicate this all on saying, how many nights does it take under a fixed selection approach to capture 50% of migratory passage? How many nights under dynamic selection does it take to capture 50% of passage in a given area? What we find using basically 2 decades of radar data across 143 sites, that dynamic selection during the spring takes about 10 nights to capture 50% of passage. Fixed selection is nearly double that, actually. So again, you're applying action to some of those intense nights, but also some of those nights that are not so intense, just because it's a blanket conservation statement. In autumn, it's about the same. It's around 11 nights it's going to take to capture 50% of migratory passage. However, the fixed selection approach really ramps up that it's going to take probably about a month's worth of lights out initiatives, for instance, to try to protect 50% of the migratory birds passing through a given area. Okay, so it looks like this approach, if you're trying to reduce the burden on human behavior, you would sort of go this dynamic selection route. But how are dynamic alerts generated, for instance? So I'll just use this schematic to really make sure that this is clear. So just like the Denver example that I had shown, we can look at a different station. This is Brownsville, Texas for 2018. And what we're going to say is we're going to try to target the nights that capture 50% of migratory birds passing. At this site, it takes around 13 nights to capture 50% of activity. And those 13 nights are going to be spread across an interval of 30 nights. So to put this in action, we need basically a forecasting tool. An ecological forecast is needed to be able to predict those nights that are highlighted here. However, any model is going to have error in it. So depending on the error, it could be that a dynamic selection method no longer outperforms, for instance, a fixed selection approach. So we also need to put this into action, see how it performs on real data with real predictions to see, do we still get close to that 10-day, 10-night metric, or is it considerably higher and actually going beyond the fixed selection approach? So this is where some of the work that we've been doing at the Birdcast project is a collaboration between my lab at Colorado State University, the Cornell Lab of Ornithology, and the University of Massachusetts. So a question that we've had is, can we actually forecast migratory movements with a high level of accuracy and precision? So our approach here is to use radar data as a test bed and a data set that we can learn the linkages between the factors that drive nightly migration. So we use these radar data to quantify bird migration on a nightly basis, and then we link them with known drivers of bird migration. It might be air temperature, wind speed and direction, and a whole slew of other factors that have been sort of well documented in the literature as being important, driving migratory bird initiation. So we've put this into place, and this is a general schematic of how we do this. We use radar data as our training data set. We link all of those data with meteorological variables. We learn the association. We learn this association in a machine learning framework. So as long as we feel confident that we have learned the associations, we can then take that model and apply it to new forecast data. That is the forecasted meteorological variables. If we know wind speed and direction is going to be X on this given night, we can predict Y, the actual bird migration intensity. So we convert a meteorological forecast into a bird migration forecast. And this is an example of one of our forecasts. So this is a forecast for the night of April 26, 2016. So the warmer colors showing us where more migratory birds are predicted to be taking flight across the US. In this case, we trained a model, but we held out all of the data for 2016. So the model doesn't really know and shouldn't know or have any sense of what is occurring in 2016. So a true independent prediction here. And then we can overlay it with what the radar actually measured on that night. So hopefully you can see the correspondence between the really warm white areas and the correspondence of the raw reflectivity data that the radars are measuring. However, this probably hopefully feels a little qualitative. We've done this quantitatively, assess the performance, doing that same holdout procedure, hold out all of the data for 2017, make predictions, and then see how those predictions compare against the truth. And we see pretty high model performance across the years that we included in our model. So now we have a forecast tool in place. We can make predictions of some of those really intense nights of activity and then see how that performs. So we're going to go back to sort of our little sketch pad here and just to remind you how fixed selection was performing. Around 19 nights were required to capture 50% of activity, and 26.5 nights during the fall to capture 50% of activity. When we use our forecast model, put it into practice, accounting for error, that were going to make warnings that just weren't in fact part of the peak nights, for instance. These are the number of nights that it would take to truly capture 50% of migratory birds solely using a forecasted model. So it would take 13 nights, basically 14 nights of warnings to capture 50% of activity. So it's 4 additional nights in comparison to sort of our reference point or what the truth was. And then it takes 15.9 nights, basically 16 nights of warnings during the autumn. And that's 6 additional nights. But hopefully you can see that this dynamic selection approach in practice is requiring fewer nights than just blanket statements of saying, turn off your lights for the next 27 nights, for instance, which would be a fixed selection sort of status quo approach. So following forecast requires fewer nights of action to capture 50% of activity. However, this stuff isn't perfect just yet. Hopefully this plot will bring this home. Again, 50% of activity captured is an arbitrary metric. We just set that out there as a reference point to test these things. You could say we want to capture 75% of birds coming through an area. How many nights of action would that require? And that's what this plot is showing you here for spring and for autumn. So the idealized dynamic approach is sort of that perfect, oracle vision of what nights will be the highest activity. That's obviously not something we have access to in real time. On the other end of the spectrum, this fixed window selection approach does require consistently an additional number of alerts or nights of conservation action to capture comparable levels of biological activity. That is because you're capturing both the highs and the lows. There's no dynamism in that approach. And this is what our forecast model, where it's performing on these ends of the spectrum. So we're hoping as we get more data, models become more sophisticated, that this line starts to creep even closer towards this idealized dynamic approach. So, that's all well and good, but it's also really important to put some of these things out there into the public arena for action throughout the United States. And that's exactly what we've done for the last couple of years. You can go to birdcast.info during spring and fall, and you can start to see some of these migration forecasts. They're updated multiple times a day. 4 times a day, we produce bird migration forecasts with a 3-day lead time. And you can see some of what this looks like. So we predict how many birds will be flying on a given night. So this is from the spring of 2020. And you can see the magnitudes of birds flying at a continental scale or the US scale of, an estimates of 337 million birds moving through the US or predicted to fly through the US on a given night. And that's what these maps look like. And we've also converted these maps, again, just biological activity or migration intensity, into lights out warnings that can be utilized across the US as well. So the red areas being these broad areas where lights out warnings will be critical. So these things continue to grow, evolve as we learn more, as models become sophisticated. We'll be improving on these techniques and these tools in the coming years as well. So I'll leave it at that, and I just want to acknowledge support for this research over the last number of years, and then really draw attention to this work from collaborators on the paper that I had presented here, but also multiple papers here, and really a shout out to this list of actors here. So with that, I'm happy to take any questions if you have them.
Kyle, thank you very much for a very interesting presentation. I see Mark has his hand up. Over to you, Mark.
Sure. Yeah. So sorry. So thanks. That was a fantastic. I was outside on my exercise bicycle, so it took me a minute to get in after as you wound down. You wound down faster than I thought. So I have a couple questions, but one I'll just leave you with one. Is the Cornell lab of ornithology is really great at looking at using eBird to look at different species. And I'm wondering if you've thought of, or what the potential is to couple what you're doing with eBird to say which nights matter more. So it might matter more if you're seeing the mortality of a Kirtland's warbler than a yellow-rump. And using their data, you might be able to parse out what portion of that migration has birds that are of higher conservation value. That would be a very hard thing, but I wonder if you could comment on that. Thanks.
Yeah, no, I think that's a great question. Definitely something that I think has been mulling around for us for a little while in the capacity of really trying to tap into that data stream. Just because there's not, there's not many data streams that cover these large geographic areas, right? So we're limited in which tools we have. And community science data like eBird is really another staple that gets down to that species-specific level. The radar definitely doesn't tell us species-specific things. So I think it's going to be that synergy that gets to a more refined species-specific approach. There's lots of ways that the eBird data can be integrated to both inform our radar models to get better estimates of how many birds are up there, what the sizes of the birds that are on the move. But I think you're exactly right that more refined, like local warnings of these bird species are on the move. You're definitely right that it's a hard problem, right? That it's some of these species overlap in that they breed in specific areas, but then also migrate through those same areas. So trying to disentangle from what is already a very messy data set that has pretty uncontrolled for effort, right? That we have to account for effort and who's out there, who's bird watching. But I think it's on the horizon for us too, that we're starting with some local test beds of trying to bring in, we're working in Georgia right now, trying to link up the eBird data for that area to better inform when those birds are on the move, when we're making a lights out warning and saying, this is the suite of species, at least from broad strokes, that are on the move. Probably can't say it's 10 Kirtland's warblers are coming through, but we might say that Kirtland's warblers are on the move for this week or these 2 weeks.
Great, thank you.
Yeah.
Thanks, Kyle. There's not much in the chat at the moment. Is there anybody else who have a burning question for Kyle? You're welcome to unmute. You're also welcome to still type in the chat if you prefer that. While we wait for that, Kyle, earlier today, after reading your paper, I opened one of these online light pollution websites. And it sort of made me wonder, how much light is too much light at nighttime? I mean, you spoke about Denver and switching off the lights, and I was wondering, is there value in only reducing the light by, say, 50%? Do we know what effect that has on the birds?
Yeah, no, I think that's a great question. So I'll just sort of back up a couple steps. So, we put out alerts in the capacity of, we often hear sort of, if we go to a building manager and they have lights on for some economic value, right? That maybe it's advertising for their business. We're probably likely to get, we're not likely to get very far with saying, can you turn off, your advertisement for 100 nights, right? That would be the best case scenario for birds, right? That the lights are just extinguished. And that would be our hope, that'd be the best case buy-in for action. But we're sort of setting this, maybe a little bit of an academic argument here. But to say, like, if you have to balance, human interests and the interest of protecting birds, then these alerts could help in that capacity. But what we found in this Chicago example at that single building is that even reducing lights, turning off some lights on the building, when we have the number of windows that were illuminated, we could cut down basically mortality by about 60%. So going from every bay of the lights are on, or at least what we historically saw at the maximum level, and then take that down to half, we're able to, you would be able to protect a lot of birds from colliding with that structure. So even, that's sometimes, is it all or nothing type of thing, right? Do you need to get a whole city to dim their lights, or would one building have impact? And I think what we're seeing is that, one building could have a positive impact of trying to reduce lights at that building. So it's not necessarily all or nothing, or to say like if you turn off your porch light, it has no effect. Maybe turning off one porch light doesn't have a very observable effect, but it's not going to hurt things by turning it off, right? So that's sort of this collective action that we probably do need a lot of people turning off their porch lights, and probably need a number of businesses to buy in to start seeing measurable effects at broad scales from these broad tools. But everything does seem to help in this capacity.
And maybe a follow-on before we go to Mark, just because you mentioned buy-in there. I put one in the chat earlier asking, so how's the buy-in been on the forecasting?
Yeah, it's, I think, sporadic. So we've run into this, I think sometimes the alerts are maybe ahead of what electrical grids or lighting infrastructure could probably even handle at a building scale. So a lot of lighting infrastructure is pretty outdated, right? That it would be awesome if a building could tap into a stream of alerts, and when that alert's turned on, the lights go off, for instance. But that's just not the reality of how buildings are operating, right? They're paying someone to say, turn off the lights, let's leave them off for the next 2 weeks, for instance. That's a lot easier for a building to manage than having someone code something up or pay someone to watch an alert and turn it off every night type of thing. However, with that said, we've had some traction with sort of what we're calling this fixed approach of saying, turn off your lights for the next 2 weeks. We've gotten traction in cities in Texas, in the US, so like Dallas, Houston, and those are some of the big ones that we've seen, and those are basically skyscrapers that are reducing their lights. So in some cities, it's 8 to 10 buildings that are dimming their lights or turning them off for an interval of time. So but it takes a lot of effort. They don't really come just by we put out an alert and a city grabs it and does like quote unquote the right thing. It does take a lot of conversation, a lot of folks working on the ground to start those conversations with the right people that can or have the authority to make that decision. So it's definitely a long-term effort here that we're a relatively small group, and doing it at these large scales is going to take time, and probably more people on the ground, Audubon agencies, bird groups, things like that, working with local partners as well.
Thanks. Yes, Mark, you can go.
Okay, yeah. So this is a sort of a follow-up as well, is that we hear about things like radio towers and windmills causing bird mortality through collisions because the birds don't see them. And bird collisions with a 2-story convention center and a 110-story Sears tower might be very different things. And I'm wondering, are your recommendations flat, or do you make different recommendations for different building types? I would think that reducing lights on the Sears tower, but not turning them all the way off might be good. But yeah, what does your data show?
Yeah, I think that's probably maybe at the frontier of sort of where we're at, admittedly. I think there's some good work by Scott Loss at Oklahoma State University. So Scott has done some of these larger scale meta-analyses of collisions. So things like power lines, to your comment there, or wind turbines, but also collisions with buildings. And Scott looked at basically residential homes all the way up to skyscrapers. And it's hard to, with these collision data, to disentangle if they collided at night or during the day. A lot of these collisions do happen during the day as well, right? That they're birds that may make landfall and they collide with a window when they're trying to forage during the day. That's hard for us to disentangle. But suffice it to say, what Scott found is that obviously the number of collisions at an individual residential home or low-rise building is going to be lower than it will be at a high-rise building. But that's not to say that there's many more residential homes than there are high-rise buildings. So you'll get bigger bang for your buck by mitigating lights on a high-rise building than one home, for instance. So it's just going to be a lot harder to get broad action at individual homes. So if you only have an allotment of 10 buildings, you should do the high-rise buildings versus like 10 residential homes. But where that tipping point exists, I think is still uncertain. But that would be our suggestion. Whether or not it's all lights off or reducing lights, definitely a reduction will help though. I think that's what we found in Chicago. Hopefully that answers your question. If it doesn't, I'm happy to expand.
Is there anybody else?
If no one's else going to ask, someone else should ask a question here, but I'll continue to throw out questions that I have to. This is in the wacky end now. So I live in a small town, and of course, before I lived here, I lived in a small town in the Midwest, and we think of these small towns as being great places to go watch fall and spring migrations because birds drop out in the towns, and maybe because lights are an attractor. But there are adjacent woodlots that might actually be better habitat for them. And one a wacky idea would be to light them up, to create them as an attractor. Probably lots of downsides to that suggestion, but I was just wondering what your reactions to that thought is.
Yeah, no, I think that's, I've heard something similar like that, but a little different, of like trying to use lights to lead birds away from aerial threats, for instance, or pull them out of, very dense urban areas. I think that's, in alignment with your question here. I think there's some obvious downsides, right? That if those birds are being attracted encircling lights, so that's what we saw at the Tribune Light. That's a relatively extreme example, but that does happen, that the birds, they want to fly north or south, but they seem to almost get sucked into these lights as if they were a moth on your front porch, right? Another light pollution issue, but I'll digress on, as an aside. But it seems like a comparable mechanism, that the birds are attracted to the light and then they start circling it. They're still flying while doing that, they're burning energy. So that's likely that those things start slowing the pace of migration at broad scales, might increase predation from nocturnal, owls, other birds of prey. So I think those things ramp up in terms of like measurable effects that, we might not see them, dead on the ground, but they might not make it to their breeding destination, for instance. But I do agree, relative scales here, Chicago, probably has less pristine, habitat than maybe a more rural, small city that might be also photo polluted. So yeah, it's a tough question. I obviously don't have the answer to it. But yeah, I think there's still some detriment. So, blanket statement out there would be, try to reduce light pollution where we can, because that will have a net benefit, at least for wildlife.
That makes sense. Thanks.
So, Kyle, how prevalent are these radar tools that you use across the rest of the world? Is it mainly something that is prevalent in the global north, or can similar things be done in the global south?
Yeah, great question. So some of the backstory here is that the US, some of the radar things are maybe more widespread in the US, in that it's a large geographic area that's, under the umbrella of one government, basically, right? So every radar in the US is identical. You can go to Europe and do comparable studies, but then you're talking about lots of countries that operate their own radars, and you get different radars. China, Russia run their own radar systems. Obviously, those are large geographic areas. Some countries are more restrictive with their radar data, which sort of makes sense, right? Like they detect a lot of things that aren't birds and are not rain. So some countries are pretty protective of what's in those signals, for instance, like military operations, for instance. So sometimes you just don't have access in some countries to those data. So getting radar data in China is more challenging than it would be in the US. But there's good radar systems in like Australia. Has their own radar system that, again, they're going to be a little geographically biased to where people live, right? So you're going to get a coastal bias of where the radars reside. But, those are options. Japan has their radar network. South Korea, there's a number of, countries out there that have them. I don't know what the coverage is in South America and Africa at this point. I know South America has some radars, but we have had challenges of getting the data, and then if you get the data, the birds have already been removed. So meteorologists don't much care, right? That, you know, the radars aren't intended or engineered to be detecting birds, so it's noise to, you know, some parties. So it just gets removed right from the get-go, and it's not maintained. So we found that as well in some other countries. But there's lots of radars out there. It does sometimes take a local partner, though, to get your foot in the door.
Okay. Okay, I'm going to rely on people to put their hands up if they have questions. Otherwise, I'm sure Mark and I will keep on throwing questions at Kyle. It's kind of maybe peripheral to the paper, Kyle, but I was wondering, and maybe a follow-up study or something, but I was wondering if anybody's done kind of back of the envelope calculations on the costs involved of switching off the lights for during your forecasts, and also the calculation on how many or to what extent mortalities are reduced during those periods, potentially.
Yeah, I think that's the next logical steps, and sort of two different paths here. Maybe they fall under the same umbrella. It's, you know, the mortality study that Benjamin Van Doren led in Chicago, I think, is a good model example of that. Of, you know, that's one building, and at that one building, you know, there's some unique topographic features at that building, but nonetheless, you know, in 20 years or so of monitoring, you know, there's at least 11,000 dead birds at that site. Across 39 years, there's around 40,000 dead birds. When it was, you know, the building previously was very illuminated during sort of their peak operation periods. The illumination at the building has subsided in the last couple of decades, which is great. But if you start scaling those things up, right, that, you know, maybe that building is not a full representation of buildings around the world, but maybe it gives a ballpark estimate of, if you scaled that up, we would expect this number of dead birds. The economics, I think, is a challenging one. The thing that we've thought about is, you know, these same alert principles might apply to like wind energy, for instance, right? Birds collide with wind turbines. A lot of bats collide with wind turbines. And that's a more maybe obvious dollar sort of ratio, right? If the wind turbine's off, the company loses X dollars in energy production. So that's something that we've thought about too, and we reference this in the paper, right? There's a light pollution side of this, but an alert can be applied to any number of aerial hazards, and wind turbines would be one of those as well. I think the economic side definitely has a lot of room for exploration and see how this shakes out in different markets, in different scenarios.
Thank you. We maybe have time for one more question. So
I think there's one in the chat.
Oh, there we go. From Laurie Hall. Some of the maps indicated reduced activity of migratory birds in the central flyway in the Midwest. Is this a result of limited data in this region, or are there truly fewer birds migrating through this region?
I'm trying to remember which, I might scale. Lori, if you're on and would have any additional details, I can sort of try to expand on that a little bit. Admittedly, the Midwest of like the Central Flyway during the spring period in the US is a very high activity area. Generally speaking, it shows up as one of the more prominent areas of bird migration activity. During the fall, the activity will subside a bit in that large scale patterns of bird migration, basically west of the Rocky Mountains in North America, those birds shift eastward. This, you know, pertains the sort of circulations of winds through North America. So during the spring, you'll get a big boom of activity in the Midwest, Central Flyway area. In the fall, you'll get more of an eastern push. There'll still be a tremendous amount of birds coming through the Midwest area, but relative, you know, spring to fall, you'll get more activity in the spring in those regions. Again, this is all sort of predicated on there should be just more birds, generally speaking, right, during the fall, that, you know, hopefully birds produce some young and they start heading south. So you might still get more birds, but if you could have complete apples to apples, the mass of birds will be shifted a bit eastward in North America. I don't know if that helps you, answers your question, but I'm happy to expand if not. Cool. Thanks for the question.
Okay, so unless there's a burning question that somebody has, I don't see any. So we've then come to the end of our time slot. And Kyle, I'd like to thank you for a really interesting presentation. Thanks for the time and the effort and your willingness to participate, and then the time and effort that went into preparing for this. It's really appreciated. So thank you very much. And then I'd just like to remind everybody that next Wednesday we have another presentation. That is by Renato Cruzeo. And he will be presenting out of Rio, and the presentation would be on associations between socio-environmental factors and landscape-scale biodiversity recovery in naturally regenerating tropical and subtropical forests. And that is based on a paper in Conservation Letters. And that would be at exactly the same time slot. And then maybe also just keep an eye on the SEB Emerging Issues page. We're busy setting up the presentations for July and August and September. So those should be appearing fairly soon. And with that, thank you all for joining us, and hopefully I see some of you again next week. Thank you.
Thanks again. Thanks, everyone.